Okay. No, it's not actually recording. Now it is recording. All right. Did someone stop it? Maybe, I don't know. Okay, thank you for letting me know that. Yeah, we did start recording, and then someone probably stopped it. I don't know. All right. So it seems that it is recording now. All right. So again, the algorithm is needed for implementation. If I am not able to implement my concrete syntax in an unambiguous way, then I have a problem. I cannot actually implement that language, and this guy is going to implement it on, let's say, Linux platforms. He's going to understand it in a one way, and that language is going to treat the concrete syntax that I have in mind in one way, and then you are going to take it for, let's say, Windows environment, and you are going to implement it in another way. Now I have a problem. My concrete syntax has two different implementations which are conflicting perhaps with each other. So now my language is not a good one anymore, because when I work his compiler, I need to understand his thing, and when I work with his compiler, I need to understand his implementation. But the idea here was we wanted to stay away from that implementation so that that meta language can actually just be good enough for me to say, okay, hey, this is what it is doing, and he's going to implement the same thing, and he's going to implement the same thing. All right. So this is important. Now, what we are going to do is, of course, you can, in principle, you can, if you have, let's say, the way that you defined your concrete syntax, if it has ambiguities, you have a problem as a designer. This is the first part. The designer has to make sure that you don't have ambiguities, because once you have an ambiguity, implementers will actually choose a solution. So you have to remove all the ambiguities. Now what we are going to do is we are going to see if these context-free grammars are, how good are they for these type of purposes. Can I actually write something without ambiguity? And if I am not able to do that, what can I do to actually overcome that ambiguity? And we'll have two things in mind when we discuss this. One is how that grammar is actually helping me to describe what I have in mind as far as the concrete syntax is concerned. At the same time, is that implementable in an unambiguous way? All right, so this is our thing. And we said already, we are going to use concrete context-free grammars for concrete syntax, defining the concrete syntax. All right, and a context-free grammar, in principle, has the same BNF that we discussed, the Backus-Naur form. You remember we had terminal symbols, a finite set of non-terminals, and a start symbol, and a set of rules, production rules. All right. Now, context-free grammars put some constraints on the structure of these production rules. And it says the production rule should be of the form like this. This is the production rule. So you have a non-terminal terminal here that can be actually replaced by some with what we call a sentence, a sentential form, we'll call it later. And this is a string of your terminals and non-terminals. And we don't have any restrictions on the form of this string. So you might have, let's say, one terminal here, one non-terminal, and you might have multiple terminals and multiple non-terminals. And you might have a combination of terminals and non-terminals. So there is no restriction. This doesn't put any restriction on the form of this sentence. All right. So this is called a context-free grammar. And what we are going to do is we are going to say, okay, I need to actually, so why am I actually describing this or using this grammar? I'm describing what I can generate. What type of an instance of that concrete syntax can I generate? Or the other way around, if a given, let's say, if someone is giving me some, let's say, sentence, I'm going to check if this sentence can be generated by this particular context-free grammar. And to do that, we are going to use the concept of parse trees. A parse tree is a graphical representation of derivation using the production rules, starting from the start symbol. And I want to actually end up at the leaves. This is going to be, what's going on? Come on, don't do this to me. I didn't do anything. All right. Okay. I'm not touching anything. Okay, good. So this graphical representation in a tree form will have nodes that will represent the left-hand side of a production rule. So when we have a production rule of this form, so let's see, I have a production rule like this. Let's say some non-terminal. In this case, I'm going to use capitals for non-terminals and small letters for terminals, okay? So let's say that X, Y, and then I have another non-terminal, and let's say Z. Small letters are terminals and capital letters are non-terminals. All right. So this is a production rule. The parse tree representation of a derivation says, okay, let's do it this way. We take a node in this graph, in this tree, and if this node is representing this particular, the use of this particular, let's say, production rule, then it will be the left-hand side of this is going to be this guy, and the right-hand side of it is going to be the children of this tree or this node. So the internal node, each internal node is going to be the left-hand side of a production rule, and the internal node must be, in this case, a non-terminal. And then the children of these node, this internal node, is going to be the right-hand side of this production rule. And if I have a non-terminal symbol, terminal symbols cannot be an internal node. It has to be a leaf. All right, so it is obvious because I cannot replace that with another, let's say, right-hand side. Therefore, when I have a terminal symbol, then I cannot go any further than that. That must be the leaf of a tree. So if you recall, when we talk about a tree, let's say if I have a tree like this, not necessarily a binary, like this, right? This tree has 1, 2 internal nodes. The root of the tree is here. This is going to be our start symbol. And these internal nodes will all correspond to a particular production rule, the left-hand side of a production rule. And each of these children will be corresponding to the right-hand side. So the right-hand side of this production rule is going to be this part. And for this, it's going to be this part. All right. And then the leaves are here. These are the leaves. I have 4 leaves. These are going to be the terminal symbols. All right. So it's very simple. Each leaf node is going to be a terminal symbol or a token, or it could be empty. All right. Good. So in this case, what we are going to do is we are going to start. The question is going to be, when I actually have a, let's say, a context-free grammar, a CFG here, including set of terminal symbols, non-terminal symbols, set of production rules, and then a start state or a start symbol or a set of start symbols, maybe a start symbol. Okay. Now, when this is given, plus you are given an ASCII file or not tokens, a set of tokens, a list, a series of tokens. This is the order is going to be important, of course, in the list. It's not going to be a set, it's going to be a list. All right. So I'll have a set of tokens and tokens. Given these, I'm going to have a parser that will generate a parse tree. So this is my parser, and this will generate a parse tree. And this parse tree is going to be of this form, exactly as we described here. Each internal node is going to be the left-hand side of a production rule, and children of these internal nodes will be right-hand side of the production rule that node represents. And each leaf node at the end of the parsing process, each leaf node will be corresponding to a token or a non-terminal symbol. All right. Now, with the context-free grammars, let's actually go back to regular grammars. And regular grammars is a subset of context-free grammars, right? And we have seen that they are of this form, and we have seen an example of that. All right. So in principle, now what I can do is I can use this thing, maybe design an algorithm for regular grammar to start from, let's say, a start symbol, and my parser perhaps can build this parse tree. The parse tree is going to be an interesting concept. It's going to actually be later used for some other things. We are going to see that as well. For example, we are going to use it to generate code. We are going to use it to, as we'll call it, an augmented grammar. And we are going to use it for actually, let's say, checking the typing of the system. Or we are going to use it to evaluate, let's say, expressions and so forth. Now, the parser for, let's say, concrete syntax analysis is going to be verifying if the order of tokens that you received from the tokenization process is following your rules for that language. All right. Now, the idea here is this. You have to generate a unique tree given a code. So when we look at this thing here, we want to generate for this code, for a specific code here, that is output of a tokenization or lexical analysis process, I should be able to generate a unique code, a unique tree. If I am able to generate more than one tree using my, let's say, analysis, then we have this, what we call this ambiguity. So ambiguity means, or at least let's start with this one. If I am able to actually generate a unique tree, that's good for me. That means that now I have one way of actually taking those tokens and mapping that to my concrete syntax in only one way. That unique parse tree says there is only one way. If it actually fits my concrete syntax, or if it is an instance of my concrete syntax. If it is not, then I'm not going to be able to get a tree at all, a parse tree, and therefore I'm going to reject that token, set of tokens, or list of tokens, or sequence of tokens, because I cannot explain it with my concrete syntax. So now we are going to say, okay, if I'm able to get a unique tree, unique parse tree, for each concrete instance, each correct instance of that concrete syntax, then I am fine. Then I can actually now take that and I can put my program as a collection of parse trees, perhaps, rooted at the top of a special, let's say, start symbol, perhaps program, and then I'm done. So now we are going to explore if, let's say, context-free grammars gives us all unique parsers, any grammar, or any, let's say, instance of a, or any instance of a grammar that we can generate with using context-free grammars. Would that actually map to a unique parser, or is it possible to expect a unique parser? Now, the idea is going to be also, once I can say that a unique parser can be generated with an algorithm, that's my goal, I need to have an algorithm, then I can build that algorithm once, and once you give me your BNF, your concrete syntax in BNF form, I can ask my algorithm that, let's say, language interpreter, if you want to call it, to generate the code for generating that parser for your language. So this will be automated as we have done it for lexical analysis. All right, hopefully, this is the aim. If I have that one, then I'm done. I give you, let's say, this tool. I say, okay, hey, here is a tool. If you can write your concrete syntax in a specific form of this BNF, then we are done. You take that, you actually write that write those BNFs, and then the tool takes it and actually converts it to a C code, for example. And the C code will take your tokens and will give you the, let's say, parse tree at the end. All right. The question.
Do we have one parse tree language compiling different C++ files at the same time?
So, if I got the question right, you are asking if we have a single parse tree when we compile, let's say, a C program. Different C programs at the same time.
Yeah, like Makefile.
No. This has nothing to do with Makefile. So, come on, don't do this to me. All right. Oh, I think I am touching this cable now. Let me see. The problem is with the cable. I was thinking that I'm not touching anything here, and this is still doing it. All right. So let it find its way. Okay. Now, assume that for the time being, our program, whatever program that we have, so there are several things going on here. Assume that we have a set of ASCII characters representing our program, and it's a single file for the time. Assume it's a single file. Multiple files constituting a program is actually a pre-processing thing. It's not actually a big deal, but assume that we have a single file. All right. If you have several files, then perhaps what you are doing is you are running concrete syntax analysis for each of those files, and then you are getting unique trees for each, and then you are combining them for whatever purposes. All right. We are not interested in that complexity for the time being. We are assuming that, let's say, I have a single file. But in principle, you can assume that all those files that you are thinking about, you can put in a single file as well. You can combine them. That's a convenience for the programmer to actually split things that way. From the compiler's perspective, compiler makes it possible for you to use multiple files, but it has nothing to do with actually the parsing. Parsing assumes that you are able to actually get a series of tokens. I don't care what part of the program it is, and I can generate a single, let's say, how do I say it? A single, let's say, parse tree. But you can also, what we are going to see that we are never going to actually have a, let's say, just a one big BNF that actually handles everything at the same time. So we'll see that the BNF is going to be split into pieces. Your grammar is going to be split into pieces. You'll define a sub part or a sub grammar, let's say, that will actually check for expressions, for example. And then it will check for statements. will check for, let's say, program function definitions. It will check for, I don't know, let's say, if loops, for example, if statements. And then what will happen is that then each of these will give you, if it is possible to generate a unique tree, you'll take that tree for, let's say, if you have here, let's put it this way. So if I have, let's say, a function here, let's say void in C, something, and then I have inside this, I have an assignment statement. Give me a break. And then all right. Let's see. All right. And then I have, let's say, an expression, even as part of this guy here, an expression. I may have a tree for expression, for this one, for example. I may have a tree for assignment. Let's say part of the tree is now, it's a big tree for assignment. And then I may have these as a portion of a program function definition, a big tree, and then a bigger tree for the main program, for example. All right. So this is the divide and conquer method, and we are going to describe mostly simpler structures because we cannot actually define the entire thing. And when you look at, if you have Richie's original book, if you look at the very end of the appendix, they have a BNF for the concrete syntax for C, and it is a few pages long, quite a long thing actually. All right, so now let's actually look at an example. What I want to do is I want to actually just tackle one part of the thing. Program. This is not going to be the entire language. I'm only interested in floating point numbers. So I'm assuming that the tokenization process gives me digits, only digits. This would be actually part of, most probably, this will be part of the lexical analysis, but I can handle this with CFGs as well. Let's see if you can do that. Right. So you see an example here. I'm describing a real number. This particular thing assumes that my, let's say, my, how do I say this? My terminals are digits 0, 1, 2, 3, and 9, and a dot. That's it. These are my terminals. My non-terminals are digits, which has 10 rules. And then I have a fraction, which actually is either a digit or a digit followed by a fraction. And then I have an integer part, which is a digit, and an integer part with digit, and a real number that goes to integer part dot fraction part. All right. So this is a simple definition of a concrete syntax of a floating point number. All right. This is not that useful, as I said. Probably you can do this with, let's say, with regular expressions, and you can do this as part of your tokenization process. But nonetheless, we can try. All right. All right. A sample parse tree for 3.14 is like this. So how did I get this one? I know that my parse tree for this particular BNF should have at the root my start symbol. And at the children, the leaf, I will have all my non-terminals, terminals, sorry. And any internal node is going to be a non-terminal. You can see it. All right. So you can see that I start with real number, and real number has only one rule to actually, you can actually, since the root has to be a start symbol, and real number is your start symbol, there is only one way that you can actually fill that thing. You have to have a real number, and you have to have 3 children. The first children is integer part, The second children is a dot, a terminal, and the third children is fraction, which is a non-term. And then now for integer part, of course, you have two options. You have either digit or integer and digit. Okay, in this case, digit will be sufficient to actually capture 3 points. All right, and then fraction part can be either directly digit or digit followed by a fraction. In this case, the first one is digit followed by a fraction, and then the fraction goes to digit and digit goes to 4. So this is a concrete an instance of this language, and you generate a tree, parse tree. The question is this parse tree unique? Can I generate perhaps another parse tree? Right. So this is one question that I can ask. Looking at this one, for this at least for this case, is it possible to generate another tree? I cannot see it right away. Perhaps it is. You have a question?
Yeah. Why is the fraction part? We got 4.
Yes.
So it's the digit. So why we have? Let's say that it's a fraction.
That's the definition, right? So definition says up to here you are okay, right? So let's see. Up to here we are all okay. Now let's say this one is okay too. You are saying that integer part. I'm looking at this integer part. Now I'm gonna say, okay, which rule can I use to actually further derive this so that I reach two terminals at my children? All right. There are two possibilities. Either integer part goes to digit, or integer part goes to integer part and digit. So I can try both of them. If I try the integer part goes to integer part and digit, I have in my input, I have this. My input is 3 dot 1 dot and 4. So this part is not gonna be actually expecting two digits on the integer part. I have 1 digit. Therefore, this will be the only possibility that I can actually derive this. Similarly here, fraction part is now this part. I have this input remaining. I can use a digit for 1, but I cannot use just 1 digit because I have 2 digits remaining here. Therefore, I have to use this second rule here. Fraction goes to digit and fraction. And then once I have the first digit handled, the second digit will be that fraction itself, right? So this is I'm not still describing you an algorithm. This is we are just kind of hand waving here right now. We are going to talk about the algorithms in a few minutes. All right. But the question was, do we have a unique tree for this input? Why are we interested in that? Again, if I have a unique tree, unique parse tree, I can perhaps now interpret this in a way. I can say, hey, I know that now if I have these literals, these things, I can put a meaning to this one. I can take this parse tree, say, okay, I know what's going on here. I have, starting from this side of the tree, I can take this one as a number, the first digit, the 10th digit. And then if I have another one here, another one here, another one here, I can actually interpret those as numbers. 10th digit, 100th digit, and so forth, and vice versa. I can take a, let's say, I can put a semantic on top of this one. But if I have two ways of this, parsing this thing or generating two parse trees, then I have to make sure that those two parse trees give me the same meaning, same semantic. Okay, this is another one. This is a little bit of a bigger one. This is describing a program. So this language is probably looks like it is a Pascal looking like thing. The language says, I have, let's look at things here, first of all. This is my one non-terminal. This is my second non-terminal, third one, fourth one, fifth, sixth, seventh, 8, and this. All right. So I have these non-terminals. And I have the terminals. Begin is a terminal, end is a terminal. This is actually a Pascal program, like a Pascal program. Pascal program starts with a begin, and then you have statements, a list of statements. And in this particular thing, what I'm going to do is I'm going to have only 3 variables allowed in this language. It's a very simplified language. So I have 3 variables. So I can use A, B, C. Okay. And then, for example, I can say, where am I? A equals, let's say, do I have an assignment statement? Yes, I do have an assignment statement. Statements list word, okay, expression. Let's say A plus B, and B equals C plus A, and end. Like this one is an instance of this language, a concrete syntax of this language. Begin is a keyword, end is a keyword, A is a keyword, B is a keyword. These are all tokens. Equality is a keyword. Multiplication, not multiplication. Addition, subtraction is a keyword. That's it. All right, fine. Now, what we are going to do is let's see if this program. I mean, I can use now this BNF, and this is my start symbol here. Program is my start symbol, and now I can actually find a parse tree for this guy. It's very simple. Since I'm going to start with a program, this is the program part. Program. This is the first node, the root node. And I have to put for the root node, I have to put my start symbol there. All right, fine. Now, start symbol, when I look at the left-hand side of my production rules, appears only in one place, in one rule. The rule says begin, statement list, end. All right, so begin. This is a keyword, a token. Statement list, let's call this SL, statement list, and then an end. Okay. Now, I have a tree, a subtree, a parse tree, sub-parse tree, needs to be still parsed further, right? Because this is not an instance that are ready for as a parse tree, because it has still leaves that, or at least one leaf in this case, one leaf exactly, that is still a non-terminal. Okay, I have to further derivate this. Okay, so let's drive it. So SL happens only in one of the production rules as the left-hand side. You see that, right? So statement list appears only in one here. So then this means that I can only use that guy. And this guy says this is a statement separated by this one, and I have a statement list again. All right. Do I have anything else? Okay. All right. I think I have something missing here, but we'll get to it. Now, this is a terminal, but I have this and this non-terminals. All right. Now, statement can be only one thing. We see it here. This is this guy. It says you have to have a variable, you have to have an equality sign, and you have to have an expression. All right. I'm still continuing. Still, I need to do the derivations. And you can see that now, if I want to put this in an algorithm, I can do the derivations from, let's say, leftmost, perhaps, or from the rightmost. Now, there is a choice that I can do. And you see that my tendency is kind of going towards leftmost, like a breadth first exploration of this tree. All right. All right. This is a simple one. We are going to see that this is not going to be possible always. So variable can be either A, B, and C. A will not work because I cannot consume this guy here. So you can see that this begin already meshed with this one. This is fine. And is matching with this one. This is fine. I have this in-between thing. And I have, after the begin, I have to have, if this wants to go to a leaf, this leaf has to be A. It cannot be anything other than A. Otherwise, my grammar is going to reject this. Okay? Since V cannot go to B and C, it can go to only A. I'm done here with this one as well. And I'm done with this guy. This is fine. Now I have E. Let's go further with E. E says I can be either variable plus variable, or variable minus variable, or variable. And I can already tell you that by looking a little bit ahead. I have this thing here. So let's take the first one at least. And I have, after the equality sign, I have A plus B. I have a few things. So it cannot be, let's say, it cannot be just a variable. You can see that, right? Or you can try just a variable, and then you'll see that it's going to fail. You're going to backtrack, and then you're going to try the second one and the third one and so forth. All right. So in this case, perhaps this could be variable plus variable, and this variable is going to be A, and this variable is going to be. And then you can continue. Of course, there is a missing problem. There is a problem here. This statement list never going to go to actually instantiate anything. So I may need to have, let's say, empty here, for example. Right. So good. So this is, you can do the derivation in two ways, either like a tree, as I have it here, or you can do it this way. You can start with a program. You can use the arrow to show that this is your, let's say, current tree with 1, 2 terminals and 1 internal node still. This is second tree where your derivation is actually taking some of these non-terminals and using that as a left-hand side of one of those DNFs and so forth. So you can actually do this and you can go this. All right. Good. Actually, I should have probably put here, instead of empty, I can put a statement here. All right. Good. So this is a derivation, but still this is not a very good algorithm because at some places I'll have multiple choices. So the question is going to be, how am I going to actually resolve those choices? Can I resolve them, or can I actually leave them to the algorithm to actually explore and say, okay, no, go back, explore, no, go back, explore. Now, the problem with this thing is, if I actually don't have an easy way to resolve which way to go here, for example, let's say when I take this one, if I have two options, let's say here, so I have two options there, I have to try those two options. And then afterwards, if I have another two options, I'm going to have 2 times 2. After that, if I have another 2 options, I'm going to do this one. So depending on the number of options that you have and the type of the, let's say the number of, the depth of the tree that you need to get, then this can go to, if you have on the average 2 options and your height is h, the number of nodes or the level, the depth of the tree is h, then you have 2 to the h different options that you need to actually try. And if you think of a C code, I can have a C code which may actually run thousands of lines of code, generating perhaps thousands and thousands of tokens. And the tree could be very, very deep. And if this goes to numbers like, let's say, hundreds, then you have a big problem, very, very big problem. So you cannot actually hope to explore all these trees and your compiler responds with a parse tree that is, let's say, unique. All right. So this is something that we discussed, if you recall. One of the considerations for a programming language was how fast, from the cost perspective, how fast is can your compiler run? if your compiler runs 10 hours to, let's say, compile a Hello World application, nobody will use that one. I mean, nobody with this, let's say, with some sense will use that. Okay, so this has to be fast. Now, the second one is, the second question we still don't answer, we haven't answered with this method. Is this going to generate a unique tree? Right? It may generate multiple trees, and we still don't know. All right. Another one, yes.
Can we, at the end of the file, we have a statement?
Yes.
Another statement. Can we have another statement list?
So if I have this one here, if I have another rule that actually statement list goes to statement, then this is what I use here. So I use statement list goes to statement. You could have actually said statement list goes to statement and a statement list, but as I said, that will actually probably not go anywhere. Or you may go a little bit further down and say, okay, hey, you'll have two answers. One, you'll start somewhere, you won't have any more tokens to talk about. You're gonna say, okay, this is not matching. Matching doesn't mean that your syntax is wrong. This means that this choice is wrong. So you backtrack and actually you do this again. So we are gonna see that by restricting your grammar a little bit, we are gonna actually make sure that things are not so difficult. So these choices, we are going to limit the choices. We are going to limit it into, and at most, let's say 1 or 2, or we can resolve them easily. We'll look into those in a few minutes. This is another one. This is just a simple assignment statement. Let's say a C-like language or syntax. You have an ID, you have an expression. ID is, this is the same thing. ID is ABC, and the expression is ID plus expression, ID times expression, expression within parentheses, and ID. All right, and you can see now, I can generate, with this one, I can generate this guy here. Okay, and I'm gonna actually use the leftmost derivation for this one. All right. So with this leftmost derivation, I can do this one. Very simple. You can see it. You have only one place to start with, right? Just this one. And then you have assignment. Assignment goes to 3 things. This is fixed, and you have an ID here, and then you have an expression here. And an ID can be by looking at the input. So your parser is going to say, okay, once I have this one, I have now what we call a sentential form. It's not a final sentence of the language or this grammar, but some in between sentence. All right. Now, but I can actually say, okay, portions of this. If I have this one, and if my input doesn't have any equality sign in it, then I have a problem. I will say, okay, this cannot be generated. It cannot go any further. This could be one algorithm. It's not a nice algorithm, though. It's still a bad one, because I need to check the entire string and then say, okay, hey, there is no equality sign, just stop it. Right? What if, of course, there are 2 equality signs there? Then you have a problem, but we'll see. Okay, and then once you say this one, you can say, okay, now I can, if I have this one, I can have only 1, 2, and 3 options here. Okay, I can only by looking at these options, I can match this guy, this token, with the option that I have. So this is good. With the leftmost derivation, I'm able to actually say that this is supposed to be A. There is no other alternative. And I don't need to go further than that. So I check 3 different alternatives. I just do a one lookup in my input. I say, okay, this is my current input. And then I'm saying, okay, for this part, for the leftmost derivation, I go this way. And ID can be only 3 things, and none of these things, or only one of these things are possible for me. So this is fine. Then this is already, since this is done, I can go to the next one. This is already done. This is the leaf. So, and this actually consumes this guy here. Now I have this left. This is my input to be parsed. and this is the rest of my parse tree to be actually built. Now, with this one, I can say, okay, what do I have? I can have expression goes to ID plus expression, ID times expression, or within parentheses expression. Okay, which one do I choose? Or ID? Why second? Why not third? No, why not first? Yes, but there is also addition. No, so I am here. So think about it this way. I am here now. Forget about this part. This is done now. So this is checked. This is finished. So I am here, and my input is this: b times, no, b times here, a plus c. Okay. Now I have three options. Expression goes to ID plus expression. Expression goes to ID times expression. Expression goes to within parentheses expression and ID. The question is, which one is possible? It's clear that this is not possible, right? That parentheses is not there in the input. I can check it. My first character is B. My first terminal is B. And this is a terminal, and this doesn't match. So I can actually reject this one. Can it be ID? If you look one ahead, you can say that. Why? You say, okay, if this is an ID, it can be an ID. But I'm looking at ahead and say, okay, hey, let's look at ID. ID says either A, B, or C. Then I'm going to say, okay, none of these going to actually happen because I have this much input waiting for me. But this is what we call with a lookup. I go one step further, and I say, oh, I cannot do it. Let's go back. All right? That's a possibility. Let's look at this one. Yes, this is a possibility, but it's going to be a dead end. We know that. How about these two? Why is this an option? This is an option clearly, right? So I can do it this way. I can say ID times expression. This is an option. And then once I go further, I'm going to realize that this is B. Now I'm done. I have this part of the expression left. So this is the right choice. But why not this is a choice? It's a choice as well. What do you mean you don't have a parenthesis? On the right-hand side here?
Yeah.
Let's clean this up and let's look at it. Why not? So we have an expression here, and our input is B times A plus C. And the question is, can this be this? ID plus expression. Can you reject this one for this input? Algorithmically, think about algorithmically. I mean, we can reject it by looking at it as a person, but our computer is not going to see it on the board like this, right? We have to find a way to actually reject this. I don't think we can reject it right away. We can only reject it at the next step. We're going to say, okay, this is a possibility, still a possibility. The only thing that I can do is I could have actually done this way. I can say, okay, hey, I'm going to have a terminal here. Do I have a terminal in the rest of my input? This terminal. Yes, I do have it here. Right? This is the only thing that I can ask. I can ask, hey, parse the rest of the input and check for this terminal. If it is there, then perhaps this is a good one. But then I'm going to realize that this will need to go to A, B, and C, whatever. And yes, it's going to go to B. But then B and plus is not there anymore. So this will be a dead end as well. But the idea here is that you cannot actually just, with this grammar, you cannot just simply reject it. You have to go one further step, and then you're going to see that that's a dead end, and you have to backtrack. And this is against the idea that we discussed earlier, right? we said, okay, we don't want to do this, all these going further explorations and coming back because it will be costly. All right. Yes. Sure. You mean for the input?
For the
ID. Okay. If you put A here, this is not going to match the input that I have. This is the input that I have. My input expects on the left-hand side a B, and you are saying it is an A. This is going to be rejected. No, I'm not going from right to left. I'm going from left to right. So you are pointing at a good, let's say, you are pointing something that makes sense. You are saying that when I actually do a parsing of the tree, we said we are going to do this one leftmost derivation, meaning I'm always going to take on the tree the leftmost leaf that actually is supposed to be derived further. But when I look at the input, what do I do with the input? Do I look at the input from the left to right or right to left? But you can clearly see that if this ID goes to whatever it goes to, if it goes to B, it's going to fail in the next stage. If it goes to A or C, it's going to be rejected in the first stage, right? So out of these two things, A is going to be rejected right away because A doesn't match the input that I have right now. Because I am looking at this tree from this perspective, when I read the leaves from this left to right, it should match with my left to right here. So this leftmost derivation assumes that I am actually also doing something on the input, and I'm doing it from left to right as well. So we are going to talk about derivation of the tree. At the same time, we are going to say, okay, how are we going to actually look at our input? And how far away we can look at that input? We are going to define those. All right. So there are two types of parsers that we are going to discuss. A parser will determine if I'm over time. Let's take a 10-minute break and we'll be starting at 9:45. You're not warning me. You're supposed to be doing like 40 minutes and then 20 minutes break, but we are doing an hour. All right. So